we'll see how quickly these hiccups go away. Hello, everyone. How y'all doing today?
We're here.
Yes, in fact. I'm glad.
If you take some water in your mouth and you turn your head upside down and you swallow while your head's upside down, it'll be really weird. And I know everyone has like a million different things that make this work, but that has never not worked for me, so I will swear that.
The thing that has always worked for me is a spoonful of peanut butter.
I would love to see you flip your head upside down. That would be funny.
It really works. Like it's so serious.
Describe this for me again.
So you fill your mouth, like you take a sip of water, but you don't swallow it, and you turn your head all the way upside down, and you swallow while your head's still upside down.
Okay.
And it is magic. Like,
Guess we'll find out.
see? I rest my case.
Okay. Okay.
Okay.
That's spooky.
This is me right now. I have no explanation for what just happened.
Write your own confused text.
Right here. I wouldn't have suggested something so ridiculous if it didn't work.
No, and I appreciate you for it, but
I can't say the
it's
same.
been a while since someone suggested something to me that was that I hadn't heard of like that, and that it worked. When in doubt, I just try to find a jar of peanut butter. I have to remember that one because if I don't have peanut butter, my trick is just to try to sit and breathe quietly. Whenever that doesn't work, that will be my next follow-up. Okay, so hiccups are gone and physics is in. Sorry, I'm just checking. One or two things. Okay, yes, I'm going to issue with the units. Okay. So, any questions at all before we get to that? Okay. To start with, we left off here where we were correlating the work done by a piston to the force the piston exerts out of itself times the displacement of the actual piston itself. And because pressure equals force over area, we can correlate this with pressure times cross-sectional area of the piston times displacement will equal work, which furthermore we can compress to work equals constant pressure in a piston times the change in volume of the piston. And this is true whether you are doing work into the piston and giving it energy, making its volume smaller, or the piston itself is doing work and its volume is increasing and it is doing work out of itself. And I actually have a kind of piston with me, and I want to demonstrate something specific with it. So when this is sealed up, this plunger will press down on the inside, compressing the gas within, and when it's sealed up, that gas can't escape, meaning that when I do work on this system and I exert a force and it compresses some distance, I'm going to be adding energy into the system. The volume will compress. Well, this particular system is unique in that the pressure is actually going to rise. It is not going to remain constant. But I like this demonstration because it does show that when compressing the piston, energy is being added into the system. So this cylinder will be filled only with air and with this tiny little bit of pocket lint that I'm going to drop inside. Seal it up. So, this is a kind of piston that is only really designed to have work done into it. It doesn't really expand much on its own. Hypothetically, if we heated it up, we could watch it expand. We add thermal energy to it, it expands and does work, but it's made of very well insulated, pretty thick plastic. So the temperature inside is designed to stay, it's not designed to let thermal energy in or out. Because the energy that is inside of it is trapped inside of it, it all tends to stay inside of the air. It's also inside of the pocket lint that I just put in there. So when I hit the piston, I'm going to do work and add energy into its contents based on the shrinking volume of the system. And the reason I put pocket lint in there is because when you add energy to it, it combusts.
Oh.
So, I hope this is visible for the entire room. I want you guys to focus right here near the base of the cylinder and try to see the pinprick of light after I actually compress it. I hope this works because sometimes it takes a million tries. There it is.
Oh.
So, that is proof that when you do work into a system, you put energy into it. Consequently, when it expands, it does work back out. Now, most real systems will usually maintain constant pressure throughout this whole process. If we were to heat this thing up, the gas inside would begin to expand, it would press harder and harder on the piston, and the piston would press out until the pressure goes back to normal at the new volume. So this particular formula up here assumes constant pressure. If you were to say heat it up and you didn't let it expand, the volume would stay the same, but the pressure would rise. So there's lots of different complex interactions that can happen here. This formula, this specific interaction, requires constant pressure and changing volume for the system to do work. As an example, let's say we have a 1 liter valve, and that valve is natively at a pressure of 1 atmosphere, and it begins to slowly expand to ½ a liter. How much work is the piston accomplishing in this situation? valve and the piston. The valve and the piston are the same thing. I apologize for using different words. So we add thermal energy into the system. It's going to expand beyond its original boundaries, but we're assuming that the pressure this entire time remains constant. So work equals pressure times delta V. The pressure can remain constant as long as it is allowed to expand to its new volume. At that volume, at that temperature, the pressures will equalize. So work is equal to, our native pressure is 1 atmosphere, and our delta V is 1.5 liters minus 1 liters. And so, our work will come out to 0.5 something. Now, pretty straightforward formula. There is one quirk about it. This will work. This method will work. It's related to the ideal gas law that we talked about in the past. The tiny problem is we multiply the liters by atmospheres, which those two things don't multiply together themselves directly to create a specific energy unit that is used in the metric system. So we have half of something, but I'm not entirely sure what. Thankfully, a conversion exists to take whatever this is, liters times atmospheres, and turn it into joules. 1 liter times 1 atmosphere equals 101.325 joules. Which means that I would actually recommend changing this formula a tiny bit. Since we want it to be in metric joules anyway, I would write this as work equals 101.325, then times pressure in atmospheres times volume in liters. Because this is functionally just a constant that we need to multiply liter atmospheres by. This version only works for liters and atmospheres, for those of the things that will most commonly be asking you to this question. So, this original version told us we had half of a atmosphere times liter. How many joules would that be?
50.66.
Very good. So, again, please, within your notes, and I'll be modifying the version I have here in the future, you can just tack right in there the 101.325 into the formula itself. I recommend that. Just have, in brackets next to it that for this precise constant to work, you want atmospheres and meters. That said, I have more atmospheres and meters to look at here. And these samples, I borrowed this from the website. These samples step through various different parts of a cycle of steps that have a piston in them. And in a real machine, if you want the piston to be doing something, like say driving the wheels of a train, it's going to go through various stages of extended, contracted, and every possible step in between, where say the temperature is being regulated or the pressure is being changed. And this question is going to take us through all those different steps, and we're going to look at what points in that cycle work is actually being done. And I'm going to roll this up so you can show a sample of gas has an initial volume of 1 liter and is undergoing a thermodynamic cycle. Find the work done by the gas on its environment during each stage of the cycle below. That's a little harder to do. The very first step is the gas is going to expand from 1 liter to 3.5 liters at a constant pressure of 6.5 atmospheres. Being given liters and atmospheres, which is exactly what we want if we want to use our 101.325 conversion to get the final answer into joules. And if this was a web assigned homework question, it is asking for the answer in joules, so we do need that little piece added on. And our starting pressure and our constant pressure throughout is at 6.5 times change in volume, 3.5 minus 1, then our adjustment factor. So the volume is going to increase as the pressure remains constant. For this to be happening, likely some thermal energy is being added to the piston. It expands and will do work on its environment. I will do work by finding where my calculator's hiding. There we go. How many joules does that give us for this step? Hmm?
1646.53.
You said 46?
Yeah.
Okay, my ears played tricks on me there. Very good. Now this is going to follow the same logic as we were using in the other first law formula. If the system is doing work, then the answer is going to be a positive number. If the piston is expanding, it is doing work out of itself, it is losing energy into its surroundings. So the piston now has used up this energy and sent it elsewhere. Positive number here will be the same as a positive work number in the previous formula. Next step. The gas is cooled at a constant volume until the pressure drops to 1.5 atmospheres. Based on this formula, is the gas doing any work? Why isn't it?
Pressure's not constant.
Pressure is not constant, while meanwhile its volume is constant. Even ignoring the fact that we don't have any term for delta P in here, our delta V term would be 0. So this particular step, flat out, the gas itself is just not doing any work. So at this particular point, whatever the system, whatever the larger machine is doing to just this particular piston, it's doing something. It's taking energy away from it, but it's not letting it do any work. It's not even doing work on the piston. It's just changing its energy level through some other means, or adjusting the pressure through some other means. The gas itself is not accomplishing anything right now.
So if pressure isn't constant, do we assume that work is zero?
Yes,
Okay.
the gas itself is not doing any work if pressure doesn't stay constant. There is a way, the real indicator is the volume change. The gas will be doing work if it is getting bigger, and it will be having work done on it if it gets smaller. There's a different formula for if the pressure changes during that cycle. So the biggest thing here is the volume change, which is why I would prefer to draw your attention to delta V being 0. Next step, the gas is compressed at a new constant pressure from a volume of 3.5 back to its original volume of 1. We are back at constant pressure and the volume is changing, so this formula works again. Our new constant pressure is 1.5. And our volume is now going to 1 from 3.5. So from the gas's perspective, what is the work in this situation?
Negative 379.97.
Okay. Very good. So since it is negative, that proves that work is being done on the piston. Energy is being sent back into it where it gave energy out before. So a different part of the machine is pushing the piston in and forcing it to be compressed in this particular moment. Part D, the gas is heated until its pressure rises back to 6.5 atmospheres. All this happens at a constant volume, so what will the work done on or by the gas be here? 0, very good. So, last question, what is the net work done by the gas on its environment throughout this entire chain of events?
Do you use the 379 as negative in this part?
You would, because we want to know the work, net work, like, throughout this entire process, the amount of actual energy we got out of this machine, just factoring in how much energy it took us to put into the machine as well. So the thing to do here is literally just add all of our previous answers together, but 2 of them are zeros and 1 of them is negative. So that would mean the net work, the actual net gain accomplished by this particular machine, would be positive 1266.
Is this a Carnot heat engine?
Yes, that's exactly what this is. This is a heat engine. This is what happens in your car or in train wheels. The term heat engine refers to a series of events much like this one, where a machine will do an amount of work, but in order to get it to do work again, you need to reset it. Let's say that this piston was a part of our machine. It's designed so that it does work when it expands, but once it's there, like if this is literally as far as the piston can reach, then what do you do with it? You have to go through some series of events to get it back to normal. And if I was to take it as it is now and push it back to its original setting without changing anything else first, I would just have to do the same amount of work back into it. If it was at the same temperature, the amount of work it takes to pull it out would be the same as the amount of work to push it back in. And then there'd be no net work out. So what a heat engine will do is the machine will accomplish its task, then different parts of the system will cool it down so that it's easier to reset it, and then warm it back up and give it the energy it needs to expand again and do more work. So it's just a constant reset cycle. And we go through these steps so that we actually get a net gain of mechanical work out of the thing. Because if we didn't bother to cool it down and reduce its pressure, this step would have been just negative 1646, and we would have gotten nothing out of it. And these types of cycles, we'll see more of them later on. These types of cycles usually are represented on graphs. So if we were to say graph pressure versus volume for this entire cycle, the first stage, we had constant pressure and increasing volume. Second stage, constant volume, decreasing pressure. Third stage, decreasing volume, constant pressure. And then constant volume, increasing pressure. And ultimately, the amount of work actually accomplished by this machine, the mechanical work you got out of the device, is the area of the box. Is this completely foreign to anybody? Is this not making
So the area of the box is the net gain.
The area of the box is the net gain of mechanical work out of the system. Ultimately, it will take more energy than this to actually make the machine work, but that cost will be in thermal energy. So it would probably take 2,000 joules of thermal energy to make it do this, but we need it to do mechanical work. We have the thermal work to give it. So all machines will output some net amount of mechanical work, but usually it'll take more energy to get it to do that. And they all have to go through this sort of reset period, and we have to figure out the net mechanical work we actually gain from the device. How you guys doing so far? Okay. We're going, it's about halfway through the period, so I'm in favor of a brief break here because this is a good stopping point where you're going to then tie this back into the other two laws of thermodynamics and close out chapter 12 for the weekend. So, just in time for a refill. atmosphere. It's rainy, it's Thursday. I'm certainly not looking forward to that. Second, we're going to proceed, we just completely wrap up chapter 12, because we have two laws of thermodynamics left to look at, and at least one of them is not nearly as math-heavy as the one we've done so far. So, we will finish up 12 today, and that will then work on 12 homework over the weekend. And next Tuesday, we will answer any questions about that. And we will, I will go ahead and open the first test next Tuesday, but it won't be due until Friday. Any questions about anything before we continue? Okay. Well, let's get through this together. So, second law of thermodynamics says that entropy of the entire universe is only ever staying constant or rising. So in general, every single interaction, every step of a heat engine cycle, I don't know why I bother trying to look it up, will in some way, shape, or form increase the entropy of that system or the universe as a whole. If you're lucky and a process is physically completely reversible, which is to say no thermal energy is created in this process, then entropy levels shouldn't rise. They will only ever stay constant. But in the real world, does any process ever not create some amount of thermal energy? No. As long as some thermal energy is created, the process can't be completely reversible. Might be theoretically possible if you can somehow completely ignore friction, but as long as friction is there, some thermal energy will be created and entropy is always rising. What this means for this particular class, because I imagine you guys have done a lot of entropy and enthalpy work before. What that means for this particular class is all machines are going to have some efficiency. You put some amount of energy in, and because of the fact you can't always completely reverse the process because some of the energy is just going to get stuck as thermal energy, every machine will only be able to output work less than the energy that was put into it. So, in terms of the physics, you cannot construct a machine that is able to convey heat by a cyclical process from one reservoir to the other. You can't invent a machine that won't create some amount of thermal energy when accomplishing its task. We can move thermal energy around, which is what makes the heat engine cycles possible, because the premise of the cycle, the actual square drawing on the graph, is that you can remove thermal energy to make resetting easier. So we can move thermal energy, but doing so costs thermal energy. The act of moving energy around takes energy to do. If you could somehow move the energy without creating more, then you could have a reversible process where it didn't take extra energy to accomplish that feat. But since it takes energy to move energy, entropy will always rise and efficiency will always be less than 100%. As such, every machine has some efficiency rating, which is simply its output divided by its input. Whatever amount of energy you put into it will be the efficiency is just the percentage of out versus in. If you ever invent a machine with 100% efficiency, please let me know. And Using this formula as it is written, you will always get a ratio, some number between 0 and 1, but you can correlate that into a percentage. I tend to put it in a percentage. And in the real world, about 20% efficiency is usually really good. It's very rare to find a process that's over 20% efficient. I think the human body is about 20% mechanically efficient. Yes?
So I used to drive like a hybrid, and you know how like when you press the gas, it like charges the battery, or the brake, no. When I was younger, I always wondered why you couldn't have a car that like started with gas, but then the movement of the wheels could like power the car while it's already moving. Why is that not?
I'm pretty sure that is a thing.
Oh, okay.
All cars have what's called an alternator. And the function of the alternator is to try to take some of the kinetic energy of the car as you are speeding up, slowing down, and turn it into electrical energy to recharge the battery. Every car has that. Mine's not, my RAV4 is not hybrid, but it does have an alternator. That's just a standard feature, because without it, your battery would not last you very long. In fact, when your battery is dead, it usually means your alternator is dead. As long as the alternator is working, you can get some juice back. So all cars can get some energy from the alternator. Hybrids are able to perform the type of transition that you're describing. And certain low energy need situations, it can drive based on the battery, but then in higher need situations, use gas.
So like if you ran out of gas in a hybrid, could you just go under 20 to the gas station, like on just battery?
Potentially, depending on exactly how the machine works.
Because like mine was electric until 20, and then it was gas.
That sounds about right. Electric engines are very good at low speeds, and they are good for short distances. The problem is batteries are heavy. If you've ever had to replace your car battery, you definitely know this. Batteries are very dense because they rely on very dense metals to form the capacitors that make them. Comparatively, you can get the same amount of energy out of a much smaller amount of gasoline, which is the entire reason why every car is battery operated at this point. Also, lithium is expensive.
When I was a kid, I would play in the woods. And one time I found a car battery, and that was my favorite toy for like a year, was this car battery that I just lugged around the woods with me.
Okay. How big a battery and how small of a child were you? Because I had trouble pulling my full car battery out of my car last year.
I don't know how big of a battery it was, but I was probably in elementary school. It was mostly like downhill though.
Fair. I'm willing to believe that you were just a very, very powerful child.
Maybe. I also had a bocce ball that was like a favorite toy of mine.
You seem easy to please.
Apparently. Just,
Find a weird thing in the woods, mine now.
yeah.
Give her a car battery and a bocce ball and she's getting mad.
Yep.
I hope mine.
Interesting combination.
Me
We
too.
liked the bocce ball because it was filled with concrete, so if you threw it, it hurt.
They're filled with concrete.
What games were you playing in the woods?
I don't know. We also used poison ivy to like swing from the trees.
Have you not
I
had
should've
siblings before?
Sorry, I never what?
You don't have siblings?
I have a sibling, but we didn't have a forest. We had our yard.
We did that kind of mess too.
No, we had.
That said, I did break my arm climbing a tree next to our backyard fort because I, in the past, had used that tree to like, I would sit on it and it would just lean down and I would use it to get off of the roof of the tree fort. And then one day I slept. And it was Mom's birthday. It's okay, we had a party the night before. Definitely not discounting your story. either a very powerful child or a slightly atypical car battery.
Maybe it was like a boat battery, I don't know, it was not like a box thing and had a little.
That sounds right. Yeah, I'm just gonna say very powerful child.
Okay.
Stronger than I am now, so well done.
This is so random, but did y'all have a trampoline growing up?
Yeah.
Did y'all used to do the thing where you put like every ball that you own, like soccer ball, basketball, like exercise ball, like you put them all on there and jump, but you couldn't touch the balls? Just making sure that wasn't just me.
I don't know, why is the trampoline more bouncy when it's wet?
Say it again.
When it rains, like the trampoline, like.
And the water
It's
goes
greater bounce, like it's bouncier when it's wet.
We love jumping on the trampoline after that.
Yeah.
I can't think that water uniquely is doing much to it. I can only think that technically every part of it weighs more,
Okay.
meaning it's just being stretched more.
You bounce higher, that's what I know.
I just like the sound when you would jump and the water would take a minute and go.
I don't think I got on a trampoline after the neighbor kid kicked me off of his, literally with his foot.
We had a net around us.
Okay, so efficiency out divided by in. So quick question. Every machine takes an amount of energy to accomplish its task. This particular cylinder, we're going to feed 1,000 joules into it. So if we look at our efficiency formula, inf equals out over in. The input here is going to be the 1,000. That is the energy we put into it so that it does its job. Its output is going to depend on this sentence. The pressure of the system is 5 atmospheres, and the cylinder is going to expand from 2 liters to 5 liters. So pressure stays constant, volume increases. This tracks with our understanding of how a cylinder does work. And so for the out portion, I'm going to recommend we just plug our formula that we have over there just right in here. So that's going to be 5 atmospheres times our delta volume, and our conversion factor to make it joules. Oops, did I make a mistake? I do that a lot.
Right now I have 151% for.
Yeah.
Yep,
That's not right.
that's not right. So we've at least established this is not a realistic machine, because I accidentally, because I invented this problem, I was clearly not very careful, so that one's on me. Solving the top gives us about 19 point something. Thank you. Over 1,000.
Just say you put in 10,000 joules and it'll make it real.
Yeah, that would be more realistic, but let's just examine my mistake a little bit further at my detriment. So what would the inf of this particular machine be?
1.5.
Very good. 1.5, and that doesn't have any units because we just divided energy by energy.
So this
It's
would
just
be like a
ratio.
magic machine?
This is the magic machine. This would have an inf higher than 1. That means it would be higher than 100% efficiency, meaning it somehow pulls energy from nowhere. It multiplies the energy.
Do you believe in aliens?
I don't think God ever said the universe was empty. There's a lot of space out there,
Do you
and I think it
believe
is
there
folly
have
to
been-
pretend I know what's out there.
Do you believe that aliens have been to Earth? If you had to put money on it right now, like if you got it right, you would get $10 billion, and if you got it wrong, you would get nothing.
Also depends on your definition of an alien.
Like a
A living being that was
Green
not.
thing? Like a, what's the word I'm looking for? Advanced alien, not like a parasite, like a,
So no venom symbiotes.
yeah.
Okay, nuts. So you're saying in this exact moment, if I can make money by answering right,
By
there's no
answering
downside.
correctly, correct.
I mean, if there's no downside, then you might as well. You're not losing $1 billion on this bet.
Right.
You just
But
have
if-
opportunity to make.
Right, but if he said, like if he said, no, and there were, yes, and there wasn't.
You might as well forget.
So that is the end of the math that is needed for the homework, so you should be good.
Cheers. Thanks.
Welcome.
Your jacket matches.
So pneumatic cylinders
I
are
mean, your
filled
calculator too.
with like
Like,
air
pretty
gas,
too.
and
Yes.
then
Pneumatic.
hydraulic is the liquid.
Wow.
Pneumatic is of a referring to specific gas.
Hydraulic cylinders are like.
Never answered. I beat the parking garage
I
entrance
didn't
with
answer
Capewood
it.
Building
There's
B,
a lot of
property.
questions lying around. One sec.
Are you looking up?
No, I'm looking up the etymology of the word pneumatic.
Those are the tubes that they use at like the bank, right?
Yes.
Did you see
Yes,
that thing where
okay.
it's like, is it illegal to put goods in the ice tube?
I would say yes.
Please don't tell me someone you know has put a hamster in there.
No bees.
Oh, geez.
I feel like that's some kind of like terrorism on the bank workers. Hamster.
That's mean to bank workers and mean to bees. We need bees. And bank tellers.
I don't know, would the like suction kill the bees though?
I don't know, I just saw it on a, like,
Because
Reddit
those tubes
feed.
move pretty fast.
They do. Okay. I will answer your question, but between pneumatic and hydraulic. Hydraulic sounds like hydro, liquid. Pneumatic comes from the Greek word nine meaning breathe, followed by the Greek word pneuma meaning wind, so air.
The hydraulic cylinders were like the same one.
Very similarly, but that would be designed more to operate based on constant temperature, I assume, because the thermal expansion of water is not nearly as dramatic as that of gas. But it will accomplish the same thing, just minor design tweaks. I don't know what I would answer in that moment, I'm sorry. I don't know which one is statistically.
4, you have to answer 3, 2.
Yes. Okay, it's a big universe, people have reported a lot of weird things in all of the park history.
I saw a UFO one time. It was really crazy. I was at Myrtle Beach, and like I was like a huge like I don't believe in anything. My mom was like a conspiracy theorist, and so like out of protest I didn't believe in anything. But I was walking on the beach at Myrtle Beach with my friend, and we both saw it, and there was this like light that turned on, and it was like above the water, it was like this big like orange like ball, and then all of a sudden it goes like this, and it was 3 orange balls, and we were like, did that just turn into 3? What the crap is going on? Is it a plane? We're like, no, it's not a plane. And all of a sudden it went back to 1 orange ball, and we're like, oh, it's back to 1. Oh my god! And then it went and it disappeared. It was crazy.
By technical definition of UFO, that is just unidentified.
Correct. It
then
was a
yes,
UFO.
You're right.
Well, I can't see very
And
well.
I went on like the UFO reporting website, and somebody else reported it too, so I knew that I wasn't like insane.
Okay. Yeah, there's a lot of weird stuff out there, and I think it is folly to try to assume there's things we don't. To assume there isn't anything we don't understand is dumb, because I'm a physicist, and physics itself was very different 100 years ago, before Einstein. Things changed, we find new stuff. As to whether or not it's specifically Martians or Bigfoot, I couldn't say.
Do you believe in Bigfoot?
I think there's lots of things on this planet we have yet to categorize.
That's
That's a really good
You-
answer.
You just can't say yes or no to anything, can you? You
No,
gotta
that's
walk
a
the
really
line.
good
I believe in
answer.
Bigfoot. Unfact.
My expertise is this list of physics laws that humans wrote. And by the fact that humans wrote them, they aren't perfect, meaning something better, a better explanation has to exist. And I think it's silly of me to assume there's things that I can't, there's things, I think it's silly to assume there's things that exist that we can, that are, I can't talk. It's foolish to assume we know everything. I think it is wise to approach things with at least the openness to being proved wrong and finding something we could not have expected. Because who would have expected quantum mechanics 200 years ago?
So kind of like the Schrodinger's cat view. Like you know it's there, or like you don't know if it's there or not, so you just like have to.
Something's there, but I don't know what.
So like kind of an agnostic way of looking at the universe.
Maybe.
You think time travel could happen?
I'm just gonna put this on the board so I can at least make sure we ended on this note, and nothing else. I do have the personal view that whatever's out there, the universe was made by a creator, and that it's meant to make sense, if not to my brain, at least to his. I think that things were assembled in such a way so that life on this planet specifically is possible. I don't know about other planets. I was never told otherwise. And the universe is wonderful, and there's a lot of weird stuff in it that we are able to observe and try and fail to categorize.
Do you think time travel is in those weird things?
I don't think it's impossible. I just think that it's either, I don't know if it would be helpful to be able to do it. Because, just to be clear, we have now gone into not Physics 1510. We are getting into me, Prof. Hoff, and metaphysics. This is not on any assignments. I do like talking about this, just full disclaimer, this is not part of the course syllabus.
We were worried.
This will not be on any test. This will.
What about bonus questions?
You know, one time Dr. Miller put, what is the, like bonus, what is the largest dinosaur to ever live? And I had just looked that up like 3 days before, and I was like, Argentinosaurus. And I drew this like picture of it, and he was like, you're the only one that got that right. And I was like, word. So I got 6 points of extra credit on my chemistry test.
Very good. The answer is not plesiosaurus because it's categorically not a dinosaur. Neither are pteranodons, which upsets me. They're technically not dinosaurs. Anyway, time. Excuse me. When you get into upper level physics, you start talking about space-time, all one word. And it's the idea that time and space are intrinsically linked, and the flow of space-time through the universe, space-time is kind of like a natural thing that literally flows through the universe, like a river. And it flows through empty space, and then it bends around matter. That bending...
How do we know that?
Einstein, a lot of guesswork, and technically we don't know it, we hypothesize it.
So that could just be completely like made up, fabricated, like
Yes.
inaccurate.
Because we didn't have any of this stuff back in Newton's day. Newton's laws we thought were perfect, but then Einstein proved they weren't perfect with the thing I'm describing now, and quantum mechanics might eventually prove Einstein wrong. But space-time flows through the universe like the river, but it bends around matter. It can't occupy the same space as matter. And that bending is what creates gravity. So the reason mass has gravity is because it is bending space-time out of the way and literally warping other matter to drift towards it. Yes?
So like is it like the bigger the planet, the more gravity?
Exactly. The more mass something has, the more it bends space-time around it, the more gravity it produces. Which is why Movies' relationship with science is always tenuous at best, but visualizations of black holes are sometimes pretty good in films because you can literally see the space bending around the edge of the event horizon.
Okay, so if you had a planet, but it was shaped like a donut instead of a sphere,
Okay.
would you, like, if you were on the inside, would you walk like this? And if you're on the outside, you walk like that?
Okay.
That was a really good donut.
Yes, thank you. If you, okay, as long as it was made of matter and it
Right.
was
It was-
sufficiently huge to create a gravitational field, if you were standing on this edge, you should be able to walk normally around the ring.
Right.
If you were standing here, I would also expect you would be able to walk around the inner ring, but you'd be lighter here than you would here, because you'd be closer to the mass of the other side of the ring, and that would pull you up
Oh.
as this mass pulls you down. You're still closer to this mass, so this should matter more, but you'd be lighter on the inside.
That's so interesting.
And theoretically, if you were able to drift right there to the center, you could just float there forever, being equally pulled on
I
all
thought
sides.
we make donuts, but
Play Halo.
we built it.
Play Halo, they're a thing, they're weapons, they're bad. So mass bends space-time, and this creates gravity. The more mass, the more gravity. Eventually, you have so much mass and so much gravity, you create a black hole, and the space-time bends so much that light can't escape it anymore. Because time is part of this whole bending, timey-wimey thing, time also gets bent near big objects, which means that time on Earth is slower than time in any part of the space that has no planet. We have observed this with our sun. Our sun has a lot more mass than Earth, meaning it has more gravity than Earth, meaning it bends time more than Earth. We know this because Mercury is slowing down. Not because it's getting slower, but because what 1 second means on Mercury is increasingly changing based on what 1 second is on Earth.
Is that like on like Interstellar, for example?
Yes.
When they go to that planet, they're there for 3 hours and they come back and it's been like 21 years.
Yes. Again, movies' relationship with science is always tenuous at best. And the fact that Interstellar tries to quantify love as a scientific principle, that's the one part that I cannot mathematically do.
I hate that movie. I think
The
it's
rest
so
of it
stupid.
is mathematically sound in terms of big planet means slower time. And big sun means slower time. So matter bends time-space, makes gravity, slows time down. Theoretically, you can bend space-time so much, you bend it in on itself and create a wormhole. And a black hole is not a literal hole. It's just gravity that will crush and kill you. It doesn't lead anywhere, it's just gravity.
Wait, can black holes actually like draw things into them like in the movies?
Think of a black hole as a planet
Do we know that
that's
they
so big,
exist
its
for-
gravity just eats everything.
Okay.
It has so much gravity, it pulls in everything, including light.
Do we have a picture of one?
You can only see a black hole if it passes in front of other things that have light. We have a picture of a black hole in front of a nebula behind it. That's the picture we have.
I'm scared. Final question, do you watch
Hang
Rick
on.
and Morty?
I'll get there. There's another question over here, I think. Okay, the larger question. I'm still on time travel. This is a long tangent. You can bend space-time so much it creates a wormhole. Black holes aren't actually holes. It's just hungry gravity that eats everything. It doesn't lead anywhere. It's just death. It will crush you to the size of a pinpoint.
Growing.
A wormhole is actually a hole. It leads somewhere. And you make it by bending space-time in on itself to the point where it just warps you to a different part of the
We
universe.
have a picture of that.
No.
Is that real?
These are theoretical at best.
Wait, how did we get you to a different part of the universe?
Because what you've done is you've bent space-time in on itself. And when you bend space-time, it has to go to another point in space-time. Again, this is from Interstellar, so
The
10 years
paper,
past.
is that what you're about to do?
Yes.
You need a pencil.
I got one, but thank you. So let's say that a planet, a black hole, something bends, like this is the plane of space-time throughout the entire universe. It flows, it bends around planets. Something might bend it so much, the two regions of space kind of end up overlapping and punches a hole in the fabric of space-time. Go in there, come out here.
Okay. But how does that hole stay there if it comes back out?
It doesn't. The only, theoretically, black holes may only exist for attoseconds.
Oh, okay.
But if, hypothetically, you could open one big enough to step through and keep it open long enough to do so, you could end up in another space at another point in time.
Would it take you a long time to get through it?
We've never seen one. We never looked through it. Theoretically, they could be opening, sorry, hypothetically, they could be opening up all around you, but only last little
What's the difference in
attoseconds.
theoretically and hypothetically?
If it's a theory, we have some experimentation to back it up. If it's a hypothesis, you can't test it. Well, it stays a hypothesis if you can't test it.
So are black holes constantly growing since they're like drawing stuff in, but it doesn't go anywhere? Because it's not a hole.
Yes. At the core of every black hole is an amount of mass. Like there's like a planet in there. And it's just, has so much mass crammed into such a tiny space, its gravity is enormous. Its gravity is now pulling in light. And as long as things keep getting pulled in, it keeps gaining more mass, it keeps gaining more gravity, and it keeps getting bigger.
Why are we not sucked into one already?
Because we're orbiting it. Like how we orbit the sun, we believe most galaxies orbit black holes.
Oh my gosh.
So eventually we'll get sucked in?
Potentially. The thing about black holes is if you don't feed them, they die. Because for some reason, as long as it's acquiring mass, it'll keep building. But if you starve it, the mass gets so crushed and so broken down, it starts to turn back into energy, and it loses mass over time, becoming weaker unless you keep feeding it.
So if it, like, they go away though, is our whole solar system like run off? If we're not orbiting
So if
them?
we're orbiting.
As long as we have our sun, we should be fine. As long as our solar system is still self-contained, we should be fine. But theoretically, if our solar system is orbiting a black hole, and that black hole goes away, and our solar system no longer orbits it and just drifts, we should be fine as long as we still have our sun. But even if our galactic center is a black hole, we're not in any danger of it eating us or it vanishing for a very long time.
That's
And that is, well, we're about out of time. Third law of thermodynamics. You know it, you're familiar with it. One object can become less entropic as you reduce its temperature, but that energy has to go somewhere else, meaning that object now has lower entropy. So the universe stays constant. We mentioned that before. The remaining slides are just different examples, which are good for you to look at, so do check these notes as you are doing the homework. The homework is currently Tuesday. We will spend all of Tuesday reviewing things for the homework and summarizing the last 3 to 4 weeks for the first test. I will open the first test on Tuesday, but you don't have to have it finished until the end of the week, because I want everyone to take advantage of the fact there's no labs next week. And I do appreciate these questions, even if it's 30 minutes. I like talking about this. I want you guys to ask me this. I'll figure out how to tie it in somehow.
You watch our homework.
I have one.
Do you like it?
It is very mean-spirited. I dislike that about it. It is incredibly crude and mean, seemingly for no end, except because the authors think that's fun.
Do you like the science half?
Yes. I do find there is some things about it that can be enjoyed, but I think it is needlessly crude and cruel. And what's the word I'm looking for? Needlessly nihilistic in its worldview.
Like, cynical?
Yes, that.
I have one more question.
Yes.
Hypothetically, is there a way that we could like get our hands on space-time and bend it ourselves to make a black hole or a wormhole?
Theoretically, your body, you being a being made of matter, you're already bending space-time. The only ways to bend it more than one already is to have more mass or be moving near the speed of light. Theoretically, by having something with an extreme amount of mass, bending the field of space-time in a very specific way, or if you could move near light speed and bend time around the moving object, you could theoretically tear open a hole on the fan. Sorry, no.
Is that how you would have to try time travel?
Is this
That I think is the
how
only way you
flashbacks
reasonably
run so
could,
fast?
because
That's
you would need to bend time enough to tear open a hole to a different point in time, but I think history would have already accounted for that. Because in the past, that hole would have already needed to be there for you to step through it.
And there's no way you could pick what time you wanted to go to, right?
Right. And like, okay, the reason I think that even if you could time travel, it would be pointless is if time is like a river, you guys can, I'm sorry, I think you have a good day, and it bends around rocks in the river, theoretically you could form a branch of the river that just goes back and flows back to it, to the past, but I think that branch would have already always had to be there. Because if the flow of time from that point onward changed, it would change every single thing in the river moving forwards. So either time has already accounted for you going back in time and it's just a self-fulfilling prophecy, or stepping back in time will inherently change literally everything, and good luck figuring out how
It's like
to
in,
not accidentally
In game,
butterfly
when they
effect
put the
narrator out of
infinity stones
existence.
back at the exact moment that they took them,
it erases that.
to erase the bad timeline. Do you like Marvel?
Yes.
Who is your
Endgame
favorite
makes me
Avenger?
mad.
Who is the strongest Avenger? I will not take arguments on my answer.
Purely in terms of muscle and punching
No,
power?
in terms of who is the strongest Avenger. With no extra context. I have the top 3, but I think I know my top one.
Hulk.
Incorrect. That is false.
It depends on how you're
Hulk's
measuring
power level
strength.
literally rises with his rage. As long as he keeps getting madder, his strength. As long as he keeps getting angrier, his strength.
I was like, my top 3, I think, hold up, Doctor Strange, Thor, and Scarlet Witch, but I think Scarlet Witch is the strongest for positive. You
Okay.
cannot change my mind.
You have an excellent point about Scarlet Witch because she's literally altering reality.
And she is the strongest because anybody else, she could just,
If what I think I understand about WandaVision is correct, she can literally alter reality, or at least the perception of reality, which makes her absurdly dangerous. Thor is powerful because, according